Hi, welcome to this Metaballs webinar. Today we are going to talk about this particular feature in Grasshopper. It's something that is quite unusual. Actually, I've never seen a video course or something about specifically about Metaballs, but I think that Metaballs are very interesting when it comes to organic shape design. We are going to talk about metaballs in 2D and 3D, and we're going to explore how metaballs are created, the several methods that we have in Grasshopper to create metaballs. But first, I invite you, this is something that has to deal with a more generic aspect in Grasshopper. I do recommend that you visit my website, actually, where you will find a page, well, actually it's a post, which is called Grasshopper Recommended Plugins. I do invite you to have a read at this post, because here you can find a comprehensive list of recommended plugins for your Grasshopper installation, depending on your specific workflow. So if you are into architecture, for example, you might want to take a look at these plugins here. There are also more general plugins like plugins for paneling and tessellation, for handling attractors, and so on. So in case you need to know what is a good set of plugins for starting to work with Grasshopper, here you will find a comprehensive list of plugins, which is actually the setup that I use in my Grasshopper installation. Also, I do recommend that you take a look at my YouTube channel. You can subscribe, of course. I already have more than 1,000 subscribers, but anyway, here I post, well, actually it has become more difficult for me to upload videos, because I am running out of time in my days. But you will find several tutorials, for example, and one of these tutorials, especially in this Grasshopper section, is this tutorial on let me see, yeah, here it is. Well, actually it's in Spanish, but I'm sure if you take a look at it, you will be able to follow the workflow. It is on vector fields, and why am I recommending this tutorial here? Because actually, what we are going to do right now when starting to work with Rhino is start to talk about well, actually, charges. Okay, so charges are the basics of vector field interaction. So when you go into vector toolbar and you go into the vector field, for example, you will find some charges here, which are line, point, spin, and vector, and especially you will find the point charge. So in order to start understanding what metaballs are, I will start by understanding what point charges in vector fields are. So basically, when I take this point charge here and place it into Grasshopper canvas, here I have a component which asks for a point with a charge acting with a specific decay and inside a boundary region. Okay, so basically, in order to have this component running, we only need to define a point. And you see that actually there is a small icon here that scales with the zoom, so there is no chance of enlarging this symbol here. But anyway, you see that we have a point charge. The charge is +1, so you see that arrows are pointing outwards from the point. The decay is set automatically to 2, which means that the strength of this point charge is basically decreasing with the distance. And then there is the boundary, which is absent, so it means that this point charge will affect all the surrounding space according to the specific decay that it has. So basically what happens with this point charge is that in the moment we use the merge field and we go and evaluate with a field line the vector field in this specific point, you will have this line coming out from this field line component. Okay, so this is how vector fields work in general. I repeat, you have the tutorial here with more complex workflows, more complex scripts, but this is in general what happens. So here you see that this line changes according to the position of the point of the evaluation point that I'm using for the field line component. Of course, I can also set multiple points, and so I will have several lines generated each by one of these evaluation points. Okay, what happens if I select multiple charges? Then in this case, you see that the vector field is generated by merging the 2 point charges together. So the field line has started to bend according to the direction of the resulting vector field. Okay, what happens, for example, if I decide that the decay is let's say higher or lower than this value? So if I set this to 0.01 minor 2 minor 10, so this is the default value. If I decrease this, you see that the point charges are basically not lowering the strength according to the distance. So the 2 point charges both act with the same intensity at this distance as if we were closer to them. But if I increase this value, you see that the point charges start to the strength start to decrease more quickly as we move away from the point charges. So you see that it changes accordingly the shape of the vector field. Okay, and then there is the boundary. So boundary is actually a box. So if I take, for example, this point here as the center for a domain box like this one. So you see that now I have these two boxes here, and what I'm going to do, I'm going to define the domain for these two boxes. I'm going to use a symmetrical domain. By the way, this symmetrical domain is a component from Heteroptera plugin. In the maths section, you will find the symmetrical domain. So I do recommend definitely that you install this this plugin here. It's quite fundamental for many advanced workflows. So symmetrical domain asks for what's the origin, the base of this symmetrical domain, and what's the amplitude, the length of the domain. So if I set this length to 10, I will have as a result a -5 to 5. Okay, so with this x here, I decide what's the, for example, the width of the box in the x direction. So I would set this to, let's say, 11. So I have a range up to 100 for this ladder. And then I will plug this into the x. So I have these two increasing or decreasing width for the boxes. And I will do the same here. I will use the same domain for the y and for the z. So I'm creating two cubes around the 2 point charge. And I will use these boxes as boundary. So you see that actually this point here is actually pushing this point away with this line, but it stops acting as soon as it reaches the boundary of this second box. As well as in this case, you see that we have these lines stopping quite immediately when they reach the boxes here. Okay, so of course, if I increase the size of these, I will have the same behavior for my vector field, but I am putting a limit to the action of these 2 point charges here. Now, in general, this is, of course, we have here some errors because the lines are just, basically, they are not coming out from the evaluation points. But anyway, this is just irrelevant for us now. Now, this is in general what happens with these charges which are associated to points. With metaballs, basically, it's the same. Okay, so Metaballs commands in Grasshopper, you can find them into the mesh toolbar inside the triangulation group, and you will find these 3 components here, which are Metaball, Metaball T, and Metaball T custom. So first of all, let's understand what are these metaballs. I will start with a very simple script here. I will take a couple of points. Let me hide the preview of this, so I just have one, which is this one. So what happens with metaballs? Imagine that we create a couple of circles starting from these 2 points here. Let's give them a variable radius like this one. Now what happens when I take one of the points and move it towards the second point, for example? You see that the two circles are totally independent from each other. So basically what happens here is that we have two separated curves that are not interacting with each other. So they are totally independent. No one here knows that there is another curve which is present in the same working space. So there is no interaction between the two objects. Okay. What happens with metaballs? Metaballs are basically curves that are generated around points. Okay, and they are generated according to the position of the points, the charge of the points, and another parameter that we will see in a while. Okay, so there are three different components. They do the same task but with different options. Okay, so the first one is Metaball, and Metaball asks for the points that we want to have as generator for the Metaball, and then it asks for X. Now Metaball is actually a component that generates one Metaball curve per each evaluation point. It's like having the evaluation points for the vector field as we were seeing just a while ago. So we need another point container, which we will plug here in the X input, and we will set one point like this. Okay, and now you see that we have this Metaball curve starting exactly at the level where this point is located. Now, what happens if I move this point closer to one of the two generators here? You see that we have two circular curves, basically. Okay, what happens if I take one of the points and move it towards the other? Now, when these 2 points start to have a, let's say, start to be close enough, let's say so, you see that the two circular curves start to deform. Okay, so actually these are not circles. Okay, these are curves that represent a charge around these 2 points here. Okay, so when these two curves or these two generators here start to get closer, the field that is generated by the two start to interact like if it was a vector field. Okay, but in this moment the result is not basically lines that are pushed away from the charges. These are basically iso lines. So it means that, for example, at this distance from the two generators, we have the same potential for this Metaball curve. Okay, so when these 2 points start to get closer, these two curves start to merge into one single curve. So it's like having an isopotential curve around the generators, and this happens whatever set of points we decide to use. Okay, so you see that in this case we have this interesting interaction between these 5 points that I have picked. And in this case, the method for creating the curve is this point. So if I move this point away, the Metaball curve will enlarge. If I move this point closer to one of the generator, then this Metaball curve will shrink around the charges. Okay, and eventually will split into several curves, each one surrounding one of the generator points. Okay, so you see that it's very nice to work with metaballs because of this behavior here that tends to create merge one single into one single shape, complex shape, organic shape, several curves according to the distance and to the position of this evaluation point. We will discuss the other two inputs later on. Okay, now this is the first method for creating the metaballs. It's quite pretty straightforward, quite simple. Let's move to the second one, Metaball T. Now Metaball T is basically the same behavior like in general. Oops, let's set multiple points so we can work with several of them. And you see that we already have circles now here. We don't need another evaluation point because this Metaball T works exactly with T, which is threshold. So threshold sets the strength or the intensity of these Metaball curves. So remember that we were talking about like iso curves or equipotential curves. So this is the meaning of this threshold here. Threshold is set to 0.5. This is a very important parameter because it keeps on popping up in several situations with several plugins. If, for example, also in 3D, as we will see later on. Okay, but anyway, what's the meaning of threshold? Now it is set to 0.5. I would set this to a value of a range of let's say 0.01 up to 10. Let's keep it like 0.5 for now, so nothing will change. And you see that if we decrease this value, these curves start to enlarge. Okay, if we increase this value, the circles or the circular curves start to shrink around these points. Now, one might think if I decrease the threshold, these curves should scale down. If I increase the threshold, these curves should increase their size, but actually it works on the opposite. So if I increase this value, they become smaller. If I decrease the value, they become larger. So it is like if this was the strength or intensity, like in terms of how much quality we want to consider when evaluating these Metaball curves. Okay, so for example, let's create one single set here, like for example, yeah, like this. Okay, and you see that with this parameter here is affecting the size of the Metaball curve. So it's like having one point moving away or closer to the generator points. Okay, and then there is the third component, third Metaball component, which is Metaball T custom. Now this is much more interesting from a certain point of view. So I will just take 2 points here, just in order to don't have to mess with the parameters. You see that there is also a threshold here, so I will set this threshold to the same range, like 0.01 up to, well, 10 it's eventually too much. 10 would work with a very dense point cloud where charges are very close to each other, while in this case I would set this to 2, for example. Okay, and you see that this Metaball T custom is still asking for a missing parameter, which is C. So C is a list of charges which can only be positive, while the point charges of vector fields can also be negative for attractor points. In this case, we can only work with positive charges. Okay, and we must provide one charge per point. Okay. So let's say, for example, that I have 2 points here, and I want a charge of, let's say, 2.00 and another one 5.00. Okay, so this would be first value, and you see that it becomes red because it is saying that we must supply the equal numbers of points and charges. Okay, so as soon as I plug this, I will have this curve coming out from this Metaball T custom. And you see that the first point, which is this one, we can eventually use the point list in order to see this. 0.0, 0.1. Okay, so the first point is this one, and we plugged the first slider with a value of 2, and then the slider with a value of 5. So the first point is getting a charge of 2, and the second point is getting a charge of 5. So you see that the Metaball is larger in this area, and smaller in this area because the charge of the first point is smaller than the charge of the second point. So with this, we can define specific strength for each of our points in the Metaball T custom. And there is a general parameter, which is the threshold that affects the whole behavior for this Metaball curve. Okay, so these are basically the three components. This is the standard behavior for the three components that are capable of generating Metaball curves. Now, a few observations, and I'm going to do this using, well, actually any of these methods here will work. I want to point out some features about the Metaball curves. Okay, so Metaball curves, as you can see here from the output, are polylines, okay, which tell us that these are not actually organic curves or shapes. They are polylines, so they are made up of a series of straight segments. Okay, so if I get closer, I start to notice that there are vertices here. Okay, now this is important because if I pretend to use these things here to create some organic shapes, I might have some surprises. So for example, if I let's say I bake this, okay, and then I take this curve and I start to see that I have several hundreds of vertices all along the curve. Okay, so if I take this and start, for example, to create a closed extrusion like this, I start to get, as a result, this thing here, which is a polysurface with very narrow faces all around the shape. Okay, so instead of having an organic shape, I am getting a faceted object here. Okay, and also it should become visible if I switch to Arctic or rendered or whatever. You see that there are these stripes here all along the vertical surface. Okay, that's because this is not an organic curve, is basically a polyline. Okay, so for example, let's consider smoothing this polyline. Okay, so I will simply simplify this panel here so I don't have to see numbers, indices, and so on. What I'm going to do, I'm going to introduce the accuracy. Okay, so this accuracy is actually a value that is optional. Normally it's adaptive, so the quality of this isocurve, or this yeah, you see it calls it isocurve actually, of this Metaball curve adapts to the size basically of the curves. But this is not enough eventually, because you might notice that if I take this point, for example, and move it away, in the connection point between these two section of the Metaball curve, I start to get this kind of straight segments which look awful. Okay, so if I want to keep an organic behavior for this Metaball curve, normally what I would recommend is to convert these polylines into some organic shape, okay, like a Nurbs curve. Now, what can we do? First of all, we can adjust the accuracy eventually. Okay, so if I set accuracy between, let's use once again 0.01 to 10. Okay, so if I do this, you see that when I decrease this value, it looks like I have some regular result. If I increase this value, the polylines start to be more, let's say, less accurate. Okay, so accuracy doesn't mean that the higher the value, the more accuracy I get. It's the opposite. Okay, so you see that the higher this value, the fewer vertices I have for this polyline. The smaller the value, the more vertices I get. Okay, so if I take a discontinuity comment, for example, you see that this is showing us how many vertices we get for this polyline. Okay, now when we start decreasing this slider here, you see that many vertices tend to disappear, and it doesn't mean that these has no vertices. It only means that the density of vertices is too high to be visualized. Okay, so if you want to know, for example, P is the amount of vertices, I'm going to calculate the list length of these. So we are going to have an idea of how many vertices we are getting when we move this value here. Okay, so you see that it starts to increase, 240, 50, 70, 300, 400, 500, 6, 7, and then it falls down. Okay, now it falls down. It doesn't mean that we have fewer vertices if we decrease the accuracy. Okay, so it's just a visualization and a computation problem, okay, for the discontinuity component. That's because the discontinuity component works considering the level of discontinuity for C1, which is tangent C. Now, what happens, for example, if we have a set of segments like this, it's evident that we have an angle here. But when we decrease the accuracy, these segments tend to approximate this curve in a way which is way better than before. So this angle here tends to 0. So there is no C1 discontinuity, and this is not detecting all the discontinuities along the curve. Okay, so this is the reason why suddenly the amount of vertices drops from 700 to 200. Okay, so discontinuity is not a good method here for doing the operation that we want to do. But anyway, we can simply consider this in order to understand what happens with this accuracy value here. Okay, so basically what I would recommend, instead of using this discontinuity here, which gives us a variable value, for now I would rather use a divide curve component, which gives us let's say it's quite strange, this choice. Right now maybe we won't get the point of using the divide curve, but later on we will see that there is some benefit from using this component here. I'm using an 11 slider, so I have a range up to 100, and I have this variable set of points. Now the advantage is that these points are basically have an equal separation from each other. And therefore I can use, for example, a Nurbs curve. And of course this Nurbs curve must be periodic, because as we get this gap here at certain points, so I will invert this periodic value here. Now there are pros and cons for this. For example, if I start to move the points, you see that working with this divide curve gives us a very discrete jump here between having a connected Metaball curve or disconnected Metaball curve. Okay, so the transition is not so smooth. No matter what we do, we will have this kind of click here between the two situations. Okay, that's because we are relying on these points here. Okay, and these points, they have some gap between each other. So the perfect solution would be to increase the count for this point here. So in this case, we are starting to get very refined curves. This means that we are able to play with this a little more. You see that there is a smoother transition between the closed or continuous and discontinuous Metaball curve. Okay, so you see that it starts to become blobby the proper way. Okay, so that's how the Metaball accuracy work, and that's how we can refine, for example, our polyline into a continuous organic Nurbs curve. Of course, if we bake this and we repeat the same procedure, we will create an extrusion like this, you see that here we get this dense set of vertical lines, but these lines are not edges. These are all isocurves. As you can see, they are all very thin curves, all but one, which is this one, which is basically the starting point for our Metaball curve. Okay, so actually if I take the endpoints command, you see that these endpoints appear, and it corresponds to the vertical edge, the unique vertical edge. So this is basically a cylindrical surface that we see here. Okay, so so yeah, basically when we for example hide the isocurves like this, and we explode this, because remember that since Rhino 5 extrusions are treated in a different way from surfaces and solids, so I must explode this. It becomes a one single surface, and I can hide the isocurves, and I only see the edges on top, bottom, and the vertical edge. And also if I switch to the rendered or Arctic preview, you see that vertical stripes are no longer present. This is a very smooth vertical cylindrical wall. Okay, so yeah, basically now we are able to create smooth curves instead of very dense polyline curves using this conversion here. Of course, there are several ways of converting a polyline into a Nurbs curve. We can do, for example, let's just leave this here like an additional oh, let me delete this. Additional methods are, for example, the rebuild curve. Just remember that the rebuild curve normally asks for a degree. If you don't provide any degree, the original degree will be used. Now the polyline have a degree 1. So if we don't specify, for example, here degree 3, we will still be getting a polyline with the amount of control points that we decide here. So basically, if we do this, we are getting to the same result, but we can decide how many control points we want for our Metaball curve. Okay, so in this case, you see that we can also optimize the amount of control point according to the density that we want to have for our Nurbs curve. This is another method, for example, for switching from the polyline to a Nurbs curve. But there are several ways that we can use. Now, I repeat, I am using the divide curve just because later on it will become useful for other applications. Okay, so yeah, I will leave this like a reference for now. I will just move it like here and turn it off. Now let's move back to our second, the Metaball T, because in this case what I want to do, oh, of course, let's discuss this with using the three component, all the three solutions for creating Metaball curves. So I'm going to use also this. So we have the three possibilities here. Let's start with the first one. Okay, the first one is creating this Metaball curve. I don't care about it being a polyline at the moment. I just want to focus on another behavior. So you see that this Metaball curve is starting, or is using the position of this point as a generator. Okay, so what happens if I select multiple points, like for example a point here where we already have the first Metaball curve, and another point here, and another point here, which are at a certain distance and closer to this charge point. Then we have this set of Metaball curves. Okay, so this is nice because we can start drawing with Metaball curves instead of just having them coming out from a specific set of points and evaluation point. Okay, so for example, if I take a populate 2D component, okay, and I define the region as one rectangle surrounding the position of the 5 charges that I have for my Metaball curve, and I'm going to use this populate 2D as evaluation point for my metaballs. You see that this nice and complex graphics start to appear. Okay, so this is very interesting because metaballs have a very graphical aspect, so they are very interesting for creating complex graphic behaviors or complex graphic outputs. Okay, that you can use however you can imagine. For example, it's interesting. For example, if you take a look at the tutorial on vector field, the message of that tutorial is that in order to draw with vector field, the important thing is how you place the charges of your vector field. So for example, if here we start to place these charges in a controlled way, then we will start to create some control design. Okay, and it's interesting because once you have this set of metaballs, it doesn't matter if they are polylines or not. In this moment, I will simply bake them as a group because they are lots of curves. You see that here we have them, and we can take these curves and, for example, export them. Let's export them like let's see, I will go like here and here and here and eventually here, and I would use, for example, the Adobe Illustrator like the format for this export here, and I will name this Metaball test. Okay, so I'm basically exporting the vector, and I can open this vector into Illustrator, for example, and treat them as any other graphic vector. This is very complex to draw in Illustrator, of course, but it's very simple to draw this kind of graphics with Grasshopper and Metaballs. Okay, so this has a very interesting graphic output. Okay, so if you want to play with these Metaballs here. So basically, in this case, the interesting parameter is the x, which are the intersection for our isocurves. Okay, now this is a very complex set of points, and it's very random because populate is a random function or pseudo-random function. But what I might do is create, for example, a line and set one line from this point, for example, or any of these points out like this, and then like divide this curve here and use the division point as generator for our curves. So you see that now we have a more regular aspect for our isocurves or Metaball curves, and you see that we have a more controlled graphic here coming out from this Metaball component. And we can always work with our point, or we can also specify multiple points, like having first one more or less coincident with the existing one, and then we can, for example, create like some weird thing like this. Okay, now you see that it's very interesting and nice to play with 2D metaballs with this standard Metaball components. So I will leave this as the final example for the first Metaball component here. So the Metaball. And let's see how this applies to the second method, which is the Metaball T, which I found way more interesting than the standard Metaball component. Okay, so in this case, for example, I'm going to turn this on. The value or the parameter that is determining the position of this Metaball curve is the threshold. Okay, now threshold is a value, a number is a floating point number. Okay, and it's interesting because if you take a look, you see that 0.01 is already a very, very low, and we start to get this potato here around the whole set of points. But if we increase this, you see that already with a value of 1, we already have very, very concentrated Metaball curves. Okay, so basically threshold could be a value between 0 and 1, 1 being already enough. But this is very nice because this means that what happens if we, instead of using this slider here, we start using, for example, a series, or rather than a series, a range. Why the range? Because the range is by default limited to a domain of 0 to 1. Okay, so we are already getting a series of values between 0 and 1, which are basically, when we define the amount of steps to 10, we will get 11 results here. And so if we do this, we will have this. Now, of course, it becomes red because range is outputting the value 0. Okay, and this is saying you cannot solve for negative threshold, and it's considering 0 to be a negative threshold. Remember that threshold must be positive. Okay, so eventually here we must call with index being 0, and so we are getting rid of the 0 value, and now everything works just fine. Okay, so this is quite nice. What I'm going to do is just move this point a little closer, so to have some interference between the charges, like this. Okay. Now, why is this so interesting? Why I found this Metaball T more interesting than the standard Metaball component? Because in this moment we are using a series of value. Despite the fact that is generated by the range component, this is a series, progressive series of values. Okay, so 0.1, 0.2, 0.3, 0.4, and so on. So being a progressive series, we have a set of Metaball curves that becomes wider and wider and wider. They start to blend together, and wider they blend much more, and then blend and blend, and we get the final potato here all around the point cloud. Okay, but what happens, for example, if we don't use a linear series of values here? For example, what happens if we take the original range and we use a graph mapper, where the graph mapper, it could be a linear function. Okay, so if this is a linear function, we will get exactly the same values coming out from this component, as you can see here. But we can also take a different function. Now, what I do recommend in this case is that we don't use a function that whose graphics basically goes up and then comes down again. For example, we can use a sine function, okay? But when using a sine function, we cannot do this, because if we do this, we will have the threshold increasing, reaching a maximum value, and then decreasing once again. So we will have isocurves or metaballs that will enlarge, and then they will shrink again, and eventually they will overlap with the old ones. Okay, so I do recommend that you use only let's say increasing values. Okay, even if they are non-linear, like in this case. And being non-linear, it means that the distance or the potential of these isocurves or this Metaball curve is not, has not a constant step. Okay, so you see that here, for example, we have less difference between the first and the second step, and much more difference between this step here and this step here. So there will be much more difference of potential between the resulting Metaball curves. Okay, so if we use these values here, remember that this is considering the 0. Okay, so we should get rid of the first value, or we can move this controller here a little upward, so we get rid of the 0 value. Okay, but I do prefer to use the whole extension, vertical extension of the graph mapper, and then just get rid of the 0. And you can see that we have much more. The graphic here is spreading much more than the previous version. Okay. Now just remember that don't do this, because as you can see, you will have overlapping curves coming out. Okay. What you can do eventually is work with a huge or a bigger set of isocurve. And you can see that also in this case we have this nice behavior from this Metaball T. And also you can see whatever you can use, whatever graph you might want to use. Okay, just keep in mind, don't use, for example, like this. Okay. Also, because in this case, for example, it is getting back to 0, and we are only getting rid of the first 0 here. So the last 0 stays untouched, and it provokes this error in the Metaball T. But you can use, for example, a Bezier. If you don't have these graphs here, it's because I have installed another plugin which extends the amount of graphs that you can use in the standard graph mapper. Also, eventually, if you want to play with a much more complex distribution of values, you might want to take a look at the Heteroptera plugins. In the maths, you have the Heteromapper that allows to create a customized graph starting from any curve drawn in Grasshopper. Okay, so it's very, very interesting to work with Heteroptera. But anyway, let's leave this like this with a complex set. Well, I will use a standard function, so in the moment you open this definition, you will have it working, in case you don't have the extended graph mapper installed in your Grasshopper setup. Okay, so this is our, just forgive my OCD. Let me order this thing properly, and then yeah, okay, so this is how eventually we can work with the threshold. And then there is the Metaball T custom, where we can also work with charges. Okay, now in this case it's absolutely interesting because we have at the same time two parameters that affect the both the position of the Metaball curve by using the threshold parameter, and also the shape of the Metaball curve, which are basically the charges. Okay, so let's say, for example, that I take a new set of points like this, set multiple points like this, okay, all along a curve. Also, we can visualize this this curve by drawing an interpolate line like this, and so we have this nice organic shape here being generated by this point. I will also count the amount of points here, and what I want, well, actually let's do this, because I want a variable number of point charges for my Metaball. So I will use a divide curve for this, and I will have a variable amount of points like this. And what I want to do, I don't need to count the amount of points that I will be using, because it is defined by this slider here. So I have these, which are 40 points determined by 39 deviations for our initial spline. Okay, so what I'm going to do, I'm going to create the Metaball T custom, which is this, starting from this point. I need charges, and the amount of charges will be this plus 1. Okay, so first thing first, I'm going to use let's start with a random generator. Okay, and the number of random values that I need is these plus 1. So I have 40 values for 40 points. Okay, so the only thing that I must be sure of is that this random doesn't output any 0. Okay, just remember that the range here is set between 0 to 1. So I can also construct a domain, plug it into the range, and eventually use a 0.01 to 1 as the A value. Okay, B is by default is set to 1. So now I am sure that I won't get any 0 from this random, and I will use this as charges. And you can see that my metaballs start to appear with a varying variable size. Okay, and threshold is set to 0.5, but I know that I can set this to 0.01 up to 0.5, let's say. So you see that 0.5 is already too much for our definition. So I will plug this here and start decreasing in order to have this metaball interact with each other. Okay, so you see we start to get some kind of random thickness along this original spline here. Okay, so it's interesting because in this case we can convert any existing shape, like for example this interpolated curve, into an object which is created using the Metaball T custom generator, which are basically 2D flat curves that eventually can be used for not only for graphic output, but also for digital fabrication like laser cut and so on. So remember that these are closed curves, so we can use this boundary surface, for example, and create three-dimensional, well, basically flat but three-dimensional object like surfaces. Okay, so it's quite interesting, and also we can play with these however we want. We can decrease the amount of points, we can increase the amount of points, which is defining basically a more dense set of curves. We can also change the seed for our random. Oh, this is a seed generator. Once again, this is an heteroptera plugin. Okay, so uncertainty, and you have this seed generator here. Okay, but anyway, I do recommend that you install heteroptera. So seed generator will give us a different seed. We can, for example, refresh by hitting F5. So if I hit F5, you see that the seed is changing. Okay, sometimes you see that some surfaces get more saturated. I missed it. Let me, okay, like this one here. It means that we have some problem with duplicated curves or duplicated surfaces, but it's okay. There is no particular problem. We are working with random factors here, so you can simply just hit F5 once again until you see that the problem disappear. Or you can also plug a timer here to the seed generator, so you will have a new solution each second or each interval that you define here. Okay, so you can see that start to be very, very interesting. Just remember that this, let me place a scribble here, heteroptera plugin, so you know that in order to work with this timer here, you need the heteroptera plugin. And yeah, I didn't use it, use heteroptera in any other position in my definition. Okay, so we have this nice set of Metaball curves converted into curves. Remember that even in this case, we are obtaining polylines. Okay, so I do recommend eventually that in order to avoid this kind of weird behaviors here, I do recommend that you convert these polylines into into Nurbs curves like we did here with divide curve, Nurbs curve, okay? In order to have a smoother aspect for our organic shapes. Okay, so now these are the three ways that we can work with Metaball curves in Grasshopper. I do recommend that you just play around with these components here, because you will find that each change, each edit that you make to your definition will give you some nice and interesting results. So don't just rest with what I am saying, just take your time, play around with these values and parameters, just experiment with for example, graph mapper and several ways, different ways of providing values to your parameters, and you will see that interesting results will pop up. Now this is the very basics for our Metaball. This is the Metaball creation. Now, how can we play with Metaballs? How can we use Metaballs in order to create some interesting graphic results? Okay, I would divide this the following part into two main applications, which are basically 2D results or three-dimensional results. Okay, now the two-dimensional results are basically coincident with what we have already seen. Once you specify the set of Metaball generator, the curves that will pop up will be basically defined by the parameters that you might want to use, which are the intersection for the standard Metaball, the threshold for the Metaball T, and threshold and charge for the Metaball T custom. Okay, but when it comes to 3D, things become to be more interesting. Okay, so for example, let's discuss the last parameter for the Metaball creation, which is the plane. Okay, so let's say that I take a point container and set multiple points like this. Well, too much. Let's say I set just 1, 2, 3, 4, 5 points. Okay, so just so we have things under control and we can see what happens. Okay, so now when we use a Metaball component, for example, like this one, and we just plug this here and say we want a point like this, we have this Metaball here, and this Metaball is being created on the XY plane. Okay, and the plane is defined by this input. By default, the plane used by Metaball to generate the curve is the XY plane. Now it's very interesting to notice one thing. What happens if I take this point here, or one of these points, and move it away from the XY plane? You see that the Metaball is starting to collapse in that area. Okay, and when this point is far enough, you see that it starts to lose its power on the resulting Metaball curve. Okay, so you see that when it gets closer, the Metaball starts to take it into account. Okay, now why is this happening? This is happening because Metaball curves are affected by not only by the point. These points are basically a charge generator which acts on the surrounding of the point, but not only in the XY plane. It acts in 3D. So you must imagine that all around one of these points you will have a spherical area of influence for each of these points. Okay, so that's why it's like having a three-dimensional vector field where we decide what is the cutting plane. So this is like an intersection between a three-dimensional field and this horizontal plane, which, by the way, means that if I define this set of points, and I don't want to use an horizontal plane, but I want to use a rotated plane, I can do it by, for example, creating an XYZ vector and a normal plane which uses this vector here. I want this normal plane to be in a position which is like barycentrical, like this one. Okay, so plane normal, and what I need now is to change the normal vector in order to change the orientation of this plane here. So x, y, and z are set to 0, 0, 0, but I can change this with a slider between -1 and 1, and I will have this thing here. So you see that when we have 0, 0, 0, there is no preview for the plane normal because there is no orientation for this vector. But if I decide, for example, I want a vertical normal, the horizontal xy plane appears. Okay, and I want this plane to be the cut plane for our metaballs. Now what happens if I give this vector some inclination? For example, I increase the x component, so this vector, instead of being vertical, will be oriented like this. Okay, so as soon as I do this, you see that the metaballs start to change the shape and the creation plane. Okay, and also if I change the y, okay, we are changing the inclination of the vector around the x-axis because I am changing the value of the y component for our xyz vector. Okay, so you see that the plane input is important because it gives us the orientation of the cutting plane, the section plane that determines the shape of these metaballs, which are basically intersection curves. Okay, so what happens, for example, if we start playing with this input here, or rather with this plane input here? So for example, let's say that I want to, this is the general scenario. Okay, so what I'm going to do, I'm going to leave this as the initial example. Let's do like this. I'm going to name this plane input, so we know what we are discussing in this area, and I want to add this to the group. Yeah, sure. Okay, so this is the general, let's say, behavior or general aspects for our Metaball creation, and now we are discussing the plane input, which, because eventually it's one of the more important features of the Metaballs. Now, I am not going to work with the Metaball, with standard Metaball, because it's, let's say, it's useless to have a physical reference like an intersection point in order to create the curves. I prefer to work with the Metaball T with a threshold. Okay, so I will use now a different set of points. For example, let's also, one thing that I want to point out is this one. If I take a line and I set one point and set another point like this, okay, and then I use a point on curve, and I define a starting point, and then I define another point here, another point close, another point even closer, and then I move away. Of course, there are more intelligent ways of doing this, but I just need quickly to have this weird set of points. And what I want to do is use all of these points as generator for my metaball. Okay, so now, as metaballs are basically a vector field or a magnetic field or strength or force field, you see that even if all these points have the same charge, the fact that we have a denser concentration of points in this area, it means that the metaball will be wider in this area. and will shrink or be narrow in this area. Okay, so point density is also a way of playing around with Metaball curves. Okay, so this is just to understand this basic concept. Okay, so what we are going to do right now is, oh, by the way, the point of curve has this bug. If you don't deactivate the preview, you get this preview staying visible. But anyway, if we apply this concept when working with our plane input, what I want to do is create a populate 2D using a, let's say, a wider region. So I will set one rectangle and set it like to this size here, and I will decrease the amount of points inside this rectangle in order to don't have too much density of charges here. And I want to use a Metaball T as the generator. Okay, so you see that we have this nice set of two-dimensional curves. Okay, like this. Let's turn it off. Also, the plane is represented by this preview. I hate having this plane here, this grid visible. So normally what I do when I don't need to work with this input here is extract parameter and turn this preview off. Okay, but right now we need to work exactly with this, so there is no point in having this component here. But what I want to do is take the rectangular region that I am populating with random points and extract this parameter here, calculate the area, because I want the center point to be available here outside from the populate 2D definition. So I will get rid of this plane here because we need to work exactly with the plane. And what I'm going to do, I'm going to create a rotating plane at the center of our Metaball area. Okay, so this will be the origin of my plane, and I will eventually copy this, which is the creation of our plane normal, and use the center as the origin for our plane normal. So you see that the plane now is in the center of our Metaball, and I'm going to plug this into the plane. So you see that eventually if I set z to a positive or negative value, I get this intersection here. If I set it to 0, the plane disappears and Metaball doesn't know in which plane I want the Metaball intersection to be created. Okay, so I want, first of all, horizontal plane. Okay, and then if I move into the front viewport and start to add, for example, the x component, you see that this Metaball starts to rotate. And the shape that it's taking depends on the distribution of charges inside this region. So for example, if I take a data recorder here and I record each variation of this vector, plane, and Metaball, if I move the x component, you see that I'm starting to get this kind of thing here, which are 2 quarters of our whole Metaball region. As well as if I decrease this value, I can have the remaining 2 quarters. Okay, and so I can create this representation for our Metaball field. Of course, this is like having some kind of star-shaped Metaball representation. If I go into the front viewport, I have this radial behavior for our Metaball curves. As well as if I go into the right viewport, I can also repeat this with the y component. So I will return this to 0 and I will do this. It becomes a little more difficult to observe this because my data recorder is actually being filled with values here, but at the same time we already know what's happening here. Okay, so also in the right viewport we might be able to see this star-ish set of Metaball curves. And so this is now full of polyline curves, non-optimized curves, that have basically represented the volumetric aspect of our Metaball field, a three-dimensional field. So each time we decide the orientation of the plane, we get one of these intersections here. Okay. Of course, we can work with both values at the same time and get a denser representation of all the areas of our Metaball field. Okay. Each time we move a slider, this is storing one additional set of polylines. So we already have 5,000 polylines here. But we already have a good representation of this thing. Now, how can we, let's say, take advantage of this behavior for our, let me empty this data recorder so we can go back to our default. Oh, well, let's delete this, okay? Also, what I'm going to do, I'm going to use the default horizontal XY plane for now, because this is interesting, but we get some kind of weird representation, totally out of control, because we have no idea of what we are doing here. Okay, we only know that we have some inclination for our Metaball field. Okay, but anyway, this is totally out of control, but we can use this in order to draw things in 3 dimensions. Okay, how? Well, let's do this very easy exercise. Okay, so what I'm going to do now, I'm going to use a populate 3D instead, just using a different box, a wider box with some height, of course, and I'm using an 11 slider in order to decrease the amount of points here. Okay, and I want this box to be out and invisible. Okay, I don't want to see it. Also, I would switch to wireframe preview because I don't want to see any volumetric surfaces represented in the Rhino viewport. So what happens if I now use a Metaball T with these points here? You see that the only thing that I am getting is the intersection on the ground, because the default plane is XY plane. Okay, but if I deconstruct this box here, now I have the range for the the X, Y, and Z for our box. Okay, so if and also you can see that I have an inverted orientation, because eventually this depends on the way I picked the points, the sides of my box when I right-clicked on this and defined the new box. Okay, so that's why you have this inverted thing here. Eventually, it will be best to work with a regular box like this. You should have 0 to 25 exactly. Okay, so you now see that the z-axis is pointing upward. So how can we use this in order to work with our metaballs? So for example, this is actually the box that we are using. Okay, so this is the height of the box. There is a plugin that allows to create a slider from a variable set of values, between a variable set of values as taken as the minimum and maximum for the range of the slider, but I don't have it. So what I'm going to do, I'm going to use a different approach. I'm going to deconstruct the box as a B-rep instead that as a box. So now I have access to the edges, okay? And I'm going to identify a vertical edge. So we have 12 edges, okay? So I'm taking a slider between 0 and 11. And what I need to find is a vertical edge like this. Okay, so edge number with index 8 is a vertical edge. And if I take a point on curve, I have this point running like this. Now this edge is actually oriented downward, Okay, so eventually if I take edge 9, it would be oriented upward. Okay, so I'm going to use this edge and this point of curve in order to do this. In Grasshopper, if you don't define a plane, you can use a point. Grasshopper will interpret this point as the origin of an XY plane. So if I take this and plug it into plane, Grasshopper will use the horizontal plane at this height as the cross section for our metaball. So if I increase this value, I will have this effect here. So you see that around each of the point, a metaball curve is being created or visualized according to the cross-section plane. There is also the threshold. Remember that we can set this to a value between 0.01 and 0.5, for example. So in this case, I would take this value to a more acceptable parameter here. And so we have this behavior here. Now this is way more interesting than rotating the cross-sectional plane for our metaballs, because this gives us a continuous set of polyline curves, of metaball curves. Okay, so for example, now I am using a manual approach, so I can do this manually. I can move this upward or downward and obtain this set of curves, but I have a problem. If I want a discrete and constant step between these curves, it's impossible because I'm working with a slider. So if I take a data recorder, this becomes more evident. If I move these, I'm doing this by hand, so there is no guarantee that the separation between these curves is constant. So if I go into the front viewport, I will notice that the separation is variable. Okay. Nevertheless, this is quite interesting because I'm already obtaining some kind of three-dimensional structure from the three-dimensional set of point of the populate 3D, which is totally random. Okay. So for example, I can also create a wider set like this, and then start to have one single shape coming out from this set of points like this. It's like a volumetric set of metaballs in 3D. So this is starting to become quite interesting because I can define interesting and very complex shapes by working with metaballs, changing the intersection plane using, for example, a manual approach like this. But I repeat, I want to have some control over this creation of this curve. I want to treat them like if it was a contour. Okay, so with a constant step between the cross sections. Okay, that's my goal. Okay, so this is one method for creating this three-dimensional set of cross section. Let me name this 3D metaball like this. Actually, they are always 2D metaballs, of course, but their general aspect, when they are created like in sequence, then you get this kind of 3D visualization of the whole force field generated by the points of the metaball T. So what I want to do now is create some method for having a discrete generation of metaballs, like with a constant separation between the curves. So what I'm going to do, I'm going to use a loop. Okay. So let's do this. I'm going to use always a metaball T. And what I'm going to use, well, actually, what I can do is do like this. Yep. Let's copy paste this and let's activate it. So let's say that this value for the threshold is it's okay. what I want to do is then, instead of using the point on curve, I want to create to use a different method. So I already have identified the vertical edge. So what I'm going to do, instead of using a point on curve, I'm using now an evaluate curve component. Okay, so I'm going to reparameterize this curve, and I'm going to use a values between 0 and 1. 0 being the starting point of my line, and 1 being the end point. So you see that this is actually exactly like using the point on curve. So if I do this, I get exactly the same result. Okay, but there is a difference, and the difference is that while point on curve is basically a slider that cannot receive any custom input, meaning the value of the slider, you set it by dragging manually the cursor of the point on curve. Okay, so if I take the point on curve, the value is set by dragging this and not by any input that can come into the point on curve. In this case, we have a t parameter, and this t parameter can be fed with a changing value instead than with a slider. So I'm not going to use a slider here. What I'm going to do is I'm going to use a loop, and this loop I'm creating it with Anemone plugin. So let me look for it. Here it is. It is called Anemone, and I'm going to use the classic loop end and loop start component. Just these two things here. First of all, let's close the loop. So when this emits a value and the value reaches here, this will send the value back to the loop start. Okay. I'm going to create a toggle, and I'm going to set this to true, and I'm going to plug this here and here. So this is going to turn on or off the whole loop. Okay. Number of repeat will give us the number of Metaball curves that will be generated. So let's start with a lower amount of curve, like 11, and then we will see what happens. Now, what do we want this loop to produce? Well, what we want to have is the parameter t. So this parameter, we already know that it must range between 0 and 1. Okay, so the final result of this should be a value which starts from 0 and increases up to 1. Okay, so this 0 here will be basically 0, and we will have this counter here, which is a progressive number that now it has a value of 0, and it will increase according to the repetitions that we are having for this loop. So what I'm going to do, I just need to close this loop by plugging the counter to the D0, okay, like this. And yeah, that's it, basically. I'm done, because what happens here is that when I connect a panel here and fire the loop, you see that we have this increasing value here. Now I am getting exactly the value of the counter. Okay, so what happens, for example, because I need here values between 0 and 1. So what I'm going to do, I'm going to take the counter and divide it, by the amount of the repetitions. So if I do this, as a result, I will get 0 when counter is 0 and the amount of repetition is 11. But when this increases, it ranges up to 1. Independently from this value here, it will always end up in 1. Okay? So this is the value that I will plug into the T input of the evaluate curve. So now when I fire this, I will have exactly a contour of this metaball. I cannot use a contour command because I have no three-dimensional object here. Okay, so that's why I must create this kind of artifacts in order to create a contour. okay? But the interesting thing is that if I set this to 100, now what I'm getting here is a set of constant separate. Well, actually this is because the data recorder was active. I'm going to empty this and I'm going to repeat this loop. So now if I move closer, you see that I have a constant step between all these lines here. Okay. So now we start to have a very nice and smooth behavior for our Metaball field, basically. And it's interesting because if this is actually determining the amount of cross sections or horizontal planes that we get here, because here we have well, actually what we can do here is if we could divide this set of Metaball curves by the height. So for example, now the Metapod T is saying it's emitting 5 polyline curves because eventually we have 5 Metaball curves generated at this height, because there are 1, 2, 3, 4, and 5. Okay, but anyway, we could also separate these curves by layer, by height, which could be quite interesting. Okay, but anyway, for the moment, what I'm going to do, I'm going to decrease the amount of curves. So we have less curves right here. And also what I'm going to do, I'm going to create a three-dimensional representation for this Metaball set, like a three-dimensional object. How I'm going to do it? By extruding these curves with a specific height in the z direction. Okay, like this. Oh, remember that this extrusion is going to be are going to be very heavy because these are polylines. Okay, so what I'm going to do by now, I'm going to divide these curves and create a Nurbs curve starting from this. And I'm going to use an 11 slider. We are going to work on this a little more in a while. Okay, but here we have our Nurbs curve that we can extrude, and you see that extrusion here is working pretty fast. And of course, we must set these to periodic in order to have our closed horizontal curves. Okay. And so we have these. And now if I do this, you will see that I have this representation. Now the height for my extrusion should be determined by the amount of cross section that I am creating. Okay, and the general height of this structure is determined by the length of this edge, meaning the height of the box. Okay, so I have the edge here. I'm going to measure the length of this curve. So now I know that the height of the box is 25.79, and I'm going to divide this by the amount of repetition that I'm using here. So each surface should measure this height here, and I'm going to plug this here. And what I'm going to record here actually is this surface. So I'm going to reset the loop, which is this one. Going to reset it. I'm going to activate the data recorder, and then I'm going to set this to true. And you see that now we are getting this nice behavior. And also, if this was an architectural model, I would also do this. Let's reset these, turn this off. And also, once that we have this curve here, let's create a boundary surface like this and plug this here. So let's activate this and run the simulation. And that's it. We have this nice set of well, actually, these are surfaces, so I can use, well, in general, I would use a brep in order to avoid any surprise here. And I'm going to bake these, grouping it, and here we have our set of three-dimensional object. You see that this orange here is coming out because of inverted normals, but we can easily manipulate things in Grasshopper in order to have the proper orientation for our objects. Okay, so it's like, I don't know if you are into architecture, for example, but the Galaxy Soho from Zaha Hadid can be designed using this technique very easily. You only have to define the proper vector field or distribution of 3D points in order to create the proper set of metaballs. Okay, so it's just a quick exercise in order to just to have a general idea of what's the potential of this thing here. Okay, so we have this contour basically created using this the metaballs. So remember that in this case, for example, yeah, we can talk about contour, but we are contouring or cross-sectioning a non-existing object. Okay, so the only existing object here are the points. The metaballs are calculated each time using a different horizontal plane determined by the evaluate curve and a loop. Okay, so this could be a 3D metaballs contour. So this has some kind of let's say real life application, especially if you are into architecture or you want to create some kind of abstract shape, abstract organic shape, and you want to prototype it, for example, let's say using some type of rapid prototyping technique like laser cut, for example. This can be very useful. Just remember that in that case, if you want to work with laser cut, this division here, which is giving us the height of the extrusion, cannot be, for example, 0.75 like we already saw. It should give us a value which corresponds to the thickness of the material that we are going to use with the laser cut machine. Okay. There is also some let's say more graphic application, which can be interesting because if you are more into dynamic graphics or interaction and digital media in general, you might find it more interesting. For example, what I'm going to do right now, I'm going to take one of the examples that we already saw, like this populate 3D with a wider box like this, and I'm going to decrease the amount of points like this, and I'm going to use a Metaball T, my favorite, with this, and I'm going to use a threshold in order to have some kind of interesting shape coming out from this from this set of points. Okay, so now we have this three-dimensional region here. So what I'm going to do, I'm going to calculate the volume of this object here. So I have the center point, and what I'm going to do, I want to create some kind of animation in this case. Okay, not using the anemone loop. What I'm going to do, I'm going to use a heteroptera component which is called wandering vector. And in case you want to know what wandering vector does, I'm going to use a vector display component and visualize this vector here applied to the origin of the XY plane. Okay, so let's turn this off, and you already see that we have, we have this set of vectors here. Now I don't need this amount of vectors, I just need one. So I go here in wandering vector and set n number of vectors to 1. Now we have just one vector. What happens with this vector is that this vector changes its orientation in time, but it does it with some kind of connection between the new direction and the previous one. So you see that this vector is not jumping around like crazy, like random. Okay, yeah, it's moving randomly, but it keeps a flowing in space, like with some continuity, okay, in the variation. So that's why it's called wandering vector, because it's like anchored here and it's wandering around in 3 dimensions. Okay. So what I want to do, I want to take this wandering vector as the normal for my plane normal, like this, and you see that now it's according to the direction of this vector. You see that the normal plane is rotating in space, and I want the origin of this normal plane normal to be the center of my well, actually the bounding box of the point cloud. Okay, so I no longer need to visualize the vector display here. I'm just going to do like here in order to have things a little more understandable. Okay, so yeah, let's leave this here in case you want to activate the preview. Just remember once again that even in this case you will need the Heteroptera plugin if you want to work with wandering vector. So let me place this here, do like this, and group. Okay, so we have the plane here, and I'm going to plug this into the Metaball input, and so we have this result. I'm going to turn everything off here, and I'm going to decrease a little more the threshold, so we have this nice effect of bubbles here in 3 dimensions. Of course, we can also create a variable amount of wandering vectors. So if I set these with a slider between 1 and 10, I can also do like this, and I can create this set of metaballs, different sets of metaballs actually, each one determined by a specific orientation for the cross-section plane. Of course, in this case, what we are doing is animating the creation of our curve cloud in order to give 3-dimensionality to our Metaball field. Okay, so if I stop recording at some point, I will already have a nice representation of my Metaball field, like this, as you can see. Okay, but anyway, this is the actual result. Now that we have understood how we can play around with metaballs, we only miss one thing. We only miss one aspect of Metaball, because everything that we have done so far is based on a static set of generators of points. Okay, what happens if we change the position of the points? Okay, so for example, let's say that in this case, what I'm going to do, let me reset this to 1. But in any way, you in any moment you can switch from the panel to the slider, so you can play around with this definition as well. So what I'm going to do right now is change the perspective. So I'm going to maintain the cross-section plane constant, and I'm going to change the position of the starting point for our metaballs. So let's turn this off. And what I'm going to do let's keep scrolling down. What I'm going to do, I'm going to use an XY plane, like a constant plane, and I'm going to use a point as the start point for this XY plane. Not because I want this plane to be in this position instead of this one, but because I can move this point up and down, and I can change the height of my cross-section plane. So like this. And I'm going to take the Metaball T, and this will be the cross-section plane. So this is going to be constant. Well, constant depending on the position of the origin. Okay. What I want to do, I want to change the points actually. So first of all, let's start with a initial point cloud. What I'm going to do now is I'm going to take a populate 2D, and I'm going to use a seed generator. You already know that we need Heteropera plugin in order to work with this seed generator. And I'm going to copy all of these things instead of using a new component here. I'm going to do like this. So you already know that we will be working with this thing here. And you see that this is generating a random set of 100 points inside this region, but this random set is changing in time. Each second we have a different distribution of the 100 points. What happens if I use these as the generators for our Metaball curves? Now I need a slider for our threshold, as always. And so I will have well, in this case my region is too small, so even with 0.5 I always get this kind of huge potato here. So I'm going to use a wider region like this. So things are starting to behave properly, and also I am using a lot of points, so I'm using now a 11 slider. Okay, so now I can get some nice results. And now we are starting to understand what happens when we change this the original set of points. Now, the only problem with this is that I'm using a random function, which is the populate2D. Well, actually, it's a pseudo-random function in Grasshopper. Pseudo-random because it's based on the seed, and I'm using a random seed generator, which is another randomness factor inside my Grasshopper definition. So basically there is no connection between each of the set of points that we see here each second that passes. So let's stop this timer. This set of points here has nothing to do with this one. Therefore, if we, for example, take these Metaball curves here, we cannot design anything with them because there is no relationship between this set and the previous one or the next one. So, for example, if I try to data record these, things start to be messy very soon. Just with few iterations, you already have this kind of messy result, which can be interesting from a graphical point of view, but there is no meaning in general. So how can we get a meaningful result when working with this approach to metaballs, like changing the set of points instead than changing the cross-section or threshold? It's evident that we must come up with a solution for creating new generations of points, but with some relationship between each iteration of this populate2D generation. Okay, so what I'm going to do right now, I'm going to leave this like an example, and I'm going to implement a more interesting way of creating changes in the original set of points. Like I'm going to, well, let's always work with this populate2D here. Let's disconnect the seed because I just want to work with the default set of points. And let me get rid of the visualization of the rectangle. So what I want to do, I want to change the position of this point in time, but in a way that this point, for example, starts to move around its original position. So what I want to do is basically move these points here. How? Well, eventually not vertically like it's happening right now, because this vector is 0, 0, 10. I just want to move them around in the XY plane. So I need this translation vector to be an XYZ vector, in which Z will remain 0 while X and Y can change. So I can use, for example, a slider between -1 to 1. And I can see what happens if I start to do this. I move all the points horizontally. If I do this, I move all the points vertically. If I do this and this, I move all the points on the right, to the right, and to the bottom. Okay. So it's evident that I need, for example, if I want each point to move independently from the others, if I have this amount of points, I will need this amount of vectors. So what I'm going to do, I'm going to use a wandering vector, but in its planar configuration. Okay, how many vectors do I need? This amount of vectors. And how many vectors do I get here? 46. So if I use these and I move closer, you see that now I'm having this change in position for each of the points. Likelihood and steps, they don't allow changing the length of the displacement. Okay, this displacement will always be between 0 and 1. Okay, so what I need to do eventually is use an amplitude component and define, for example, a amplitude between 1 and 10. So this allows to use to create a more intense displacement. Well, actually I would use a 0.1 to 10. Okay, so you see that now we have this nice behavior for our points. And finally, we can use the Metaball T with this point here. So this is actually generating a real variable Metaball curves pattern in the XY plane, without having the need of creating a three-dimensional structure. Of course, in this case, if I data record these, curves will always overlap, but they will do it in a more elegant or structured way. So you can see we start to get this kind of organic pattern in the XY plane this time, which looks very nice. And as it is based on an heteroptera component, which is the wandering vector, you can be sure that if you take another data recorder and start recording these, let's wait a while before we stop recording. Now if we take a look at these two things here, you see that the pattern is different. Okay, it's totally different. This is because this algorithm is based on the wandering vector component. Everything that you use in heteroptera is, let's say, it's more random than the standard random component of Grasshopper. Okay, so it's very nice to work with heteroptera in any type of workflow, even in defining Metaball behavior. So even in this case, I will copy paste this and place it here. So you know that even in this case, you need Heteroptera to be installed. Well, actually, what I would do is this. So Heteroptera plugin needed, and group, and change the color. So it's quite evident that if you don't have Heteroptera, something bad will happen when working with this definition. And yeah, so we have this kind of, well, I will get rid of this data recorder here, but you know that in any time you can just start recording the position of this. And also you can play around with this amplitude, and also you can play around with, you already know, with the tolerance. Okay, so just remember that even with tolerance you can have some interesting behavior here, interesting variation in your Metaball curves. Okay, so for example, like this, if I increase these values very much, I will start to have a more randomish behavior for my Metaball curves. Just remember that if you want, you must always smoothen these curves, converting them into Nurbs curves instead of working with polylines, if you want a more natural or organic aspect for your curves. Okay, so very nice result here. Oh, we can give a name to this section here. This is some kind of, like Rorschach graphics here, like those that are using in psychology. So, well, actually, just let's call this random Metaball 2D. Oops, I'm not using a scribble. Okay, random Metaballs 2D. This is going to be the name of this new group, and let's turn it off. So it's quite nice. Now, the next section, what we're going to do now is, okay, we have these sets of curves, right? These Metaball curves. What can we do with them? Because if we don't want to use them as a contour curves like we have done here, for example. Here what happens is that we can use this as a method for creating this three-dimensional representation for our objects, okay, or for our virtual objects. But what if we don't want this? What if we don't want to have a laser cut model, okay? And we want, for example, build a three-dimensional object starting from this set of curves that come up from our animated Metaball creation. Now, what we can do is this. Let's repeat the procedure in order to fix this in our memory. So what I'm going to do, I'm going to set one box, and I'm going to create a box which is quite tall this time. So like some towerish shape, okay? And I'm going to extract the parameters, so I have the box available outside from the Populate 3D, and I also have this time I will use a 101 slider in order to have a top value of 1000 point for my point cloud. So you see quite a dense point cloud I can get, but I will limit for now to a smaller amount. Just remember that in Grasshopper, if everything works fine with a few geometry, it will work as well with lot of geometry. The only difference is that you are stressing the computer way too much, and eventually it might crash. So I always recommend my students that they lower the values of the sliders unless it is not strictly necessary to work with lots of geometry. And what we are going to use is a deconstruct brep, and we are going to use a list item. Remember that we're using edge number 9, which was the vertical one, oriented upward. And so with this, we can create our loop and loop end. Oh, I think I forgot to name the fact that this is anemone plugin. Okay, so these three, I will group them, and I will switch to a oh, this is interesting because actually this is a Metaball behavior. I didn't think about it, but anyway, very nice. So this is the anemone plugin. I will give a color so that things are connected properly, like this, and with alpha 255. Okay, so let's close the loop. And remember that what we wanted, oh, we need a toggle set to true and trigger and exit connected to the same toggle, and the amount of repetition that we can set to 11 for now. And what we want to do is divide the counter by the amount of repetition in order to have a value between 0 and 1 that we can use for our evaluate curve, like this. Reparameterize the curve always. Okay, so that's it for our loop, and so we are ready to work with our definition. I will move this here down a little so I have things organized once again. So we have the loop. Let's add this to the same group. Yeah, exactly. So we have this group here working perfectly with anemone. Yep, so let's move this here, and let's move this here, and let's move the group here. Okay, so we are ready now, and we can use this evaluate curve with our Metaball T. These will be the points. This is going to be the cross-section plane, which will be changing. Oh, actually, it is not changing because the counter is not connected to the loop end, so the value is not being sent back to the loop start. Now it is. Now with 11, we only have few sections, but if we change this to a higher value, then everything will work fine. And tolerance 0.5 is too much. I will set this to the usual values so we can control the intensity of our Metaball field. Okay, so here we have this nice set of curves coming out. I will eventually increase this a little more so we have more interesting result when curves split and separate from each other. We will have a more complex organic shape coming out like this. And we can also use a random seed generator. This time I won't use a timer connected to this random seed generator. I just want, oops, let me do like this. Yeah, exactly. I only want this to generate a different set of points whenever I want to create a different organic shape using this definition. So in this moment, for example, I get this, but if I hit F5 and repeat the loop, I will get a different shape. So what I want to do now is I want to take these metaballs here and data record them. So I'm going to reset these empty this, and start once again. So this is going to be the set of curves that I want to work with. Eventually, later on, we will increase this value a little more. But first of all, we want to learn how to convert this into a three-dimensional object. Okay. Now we have a bunch of problems here because this object here starts with 3 separated curves, then it becomes one single curve up to this height, and then it splits again initially into 2 and then into 3 separate curves. So there is no way to convert this into one single surface. Okay, we cannot loft, we cannot do anything, not even the patch will work in this case. Okay, so what I will do in this case is work with meshes. Okay, now we have this set of curves here, 105 curves. And first of all, we want to, the approach here is create a mesh by using these curves as original input. There are basically 2 ways of doing this. First one is using voxels. Okay, so what I need in order to work with voxels is to convert this set of curves into a point cloud. And in order to do this, what I'm going to do, I'm going to divide these curves using the divide curve component. This is when the divide curve component becomes useful for us. Okay, so eventually what happens here, and this is not evident in this moment, but if I start to increase the amount of segments here, for example with a 11 slider, and I start to increase this, I notice that the Metaball curves that are shorter generate a more dense set of points, of course. So you see that all these curves here are being divided into 52 segments, okay? But this set of points is way more dense than this set of points. This is because our curves have a different length. So now what I'm going to do, I am going to determine the amount of divisions according to the length of these curves. So I'm going to measure the length of all these curves here. So we have this range between a minimum and maximum value. Oh, by the way, also this thing here is another heteroptera plugin component. So we have the length of these curves ranges between 15 and what is this? 82. Okay. So what I want is, let's take a look and see when these the smallest curves start to have enough point density. You see that with 50 we already have a reasonable amount of point for the shorter curves. So I would say that I want to remap the length of these curves to the amount of division. Okay, so the shortest curve will be divided into 50 segments, while the longest curve we can use, for example, 100, because I see that the resulting density is comparable to the density of the shortest curve with a number of division of 50. Okay, so let's use a remap numbers. I want to remap the length with the length have an initial range between these 2 values here, and I want to remap them in a new domain which will represent the amount of segments between 50, and let's use a 101 slider here so we have more possibility of changing the amount of divisions. Okay, and so we have in this case 105 polylines, and here we have 105 remapped numbers that we can use as a number of segments for our division. Okay, so like this, and you see that this is giving us a more uniform distribution of division points. Eventually we can decrease, for example, the amount of division for the shortest curves like this, And as you can see, we can easily find a more balanced representation for our set of points. As you can see, it's starting to be very, very regular. But anyway, the point is you don't need to get exactly the same density. The important thing is that you don't have too much difference between the shortest curves and the longest curves. Okay, so that's the reason why we are remapping this number. So I'm going to, well, this is just useless for now, so I will just get rid of it. So these are the points. Now each curve is being divided into parts, so we have quite a huge data tree here, because each branch contains the division point for one of the curves. Actually, I don't need these points to be divided into branches, so I will flatten this output in order to have access to the 10,000 points that I have here. And what I want to do, I want to convert these points into one single point cloud. Okay, so I'm going to use the Volvox plugin, which is quite an interesting plugin for working with the point clouds. And I'm going to use the construct cloud component, which converts these geometric points into a single point cloud. Okay, so you see here we have 10,000 points coming in and one single point cloud with 10,000 points coming out. Okay, so this is, let me place a scribble here, so in case you don't have the plugin installed, you will at least know what plugin you need. Volvox plugin. Here it is. So now, once we have the point cloud built by Volvox, we can also use Volvox to represent this point cloud with voxels. Okay, so also this is part of the Volvox plugin, and this is asking for the voxel size. Okay, so I will set this to 1 for now, and it is generating these voxels starting from each point of the point cloud. So you can see this in 3D, and you can see we start to get this kind of three-dimensional object. Okay, now voxeling is just one quick way of giving thickness to points by adding a cube basically around each point of the point cloud. Now we can also use a bigger value for the voxel size in order to have voxel touch each other, okay, and get one single mesh from the connection of all these voxels. But you see that if you increase the size of the voxels, you get a coarse representation of your three-dimensional object. Okay, so the idea is to keep these voxels with a relatively small size and increase the amount of points of the point cloud. Now, we don't increase the amount of points of the point cloud by changing the amount of division with these two values here. We can do this by increasing the amount of repetition of the loop, which means increasing the amount of horizontal cross sections and therefore of metaballs. So I will exit the loop, increase this to, let's say, 75, delete the content of the data recorder, and then just fire this and start creating once again the three-dimensional object like this. And you can see that you get this nice representation of your three-dimensional object. Now, the only problem with this kind of generation of a 3D object by voxelizing the point cloud is that when you have a sudden change of shape in the metaballs, the points will always be separated from each other. So eventually the more horizontal portion of your three-dimensional set of points will result into these holes, basically. So the only thing that you can do here is eventually increase the size of your voxels and try to cap all these holes. But even in this case, I would recommend that you prefer a different strategy, which once again is, let's empty these, reset these, and increase the amount of cross-section that you generate. So we have a denser set of isocurves, let's call it down. So this is the problem here. You see that there is a sudden variation of size of this Metaball curves. So in this area is difficult for us to get to a continuous voxeling of this portion of our surface. Okay, so that's the problem. And eventually we will notice that even in this case, we will always get holes in this area. Okay, so the only thing that you can do here is increase the number of repetition. And in this case, don't worry too much. Well, actually, I have quite a powerful computer, but don't worry too much of the result, because yeah, even here at the bottom you see that there is already a huge gap that it's very difficult to fill. Let's see what happens here at the top. But I was saying, don't worry too much, because once you convert points into a point cloud, the point cloud is a very light object. Okay, you see we are starting to recover from this huge gap, but we still have some relevant gap in this area. So it's very difficult to let's say correct this problem here. Anyway, we can take a look, and you see that voxeling is always very quick. Okay, so just don't worry too much about this. But you see that the hole is starting to get closed. And in this case, when you have this kind of gap consisting of one pixel or one voxel, sorry, then you simply increase a little this value until you see that this hole is filled. And we are just affecting this structure by two units here. So you see that, yeah, we still have a gap here, which is quite difficult to fill, but anyway, we start to get this kind of continuous shape, voxelized continuous shape. And once you have these, you see that this is just one mesh. So these curves basically merge together once they touch each other. And so therefore you can try to take this object and start to apply some subdivision algorithm or whatever you might want to try to use in order to smoothen this object out a little. Okay, like in this case, Weaverbird's Cotton Flux subdivision. By the way, this is the plugin Weaverbird. Okay, so this is one way of converting this Metaball structure into a three-dimensional object. But you see that voxelizing this point cloud will always give this kind of discrete results. So it's like having some kind of three-dimensional contour occurring to this point cloud. That's because we are using voxels. Okay. If you want a more continuous result, like for example the one that I have used for the plugin announcement, like for example you can see it here, like this image here. It's evident that it is way smoother than the result that we are getting right now. So if you want to get to that result, you cannot use voxels, of course. Okay, so what I'm going to do, I'm going to turn everything off here, and I'm going to use another technique, which is curious, by the way, because once again it will be based on charges. Okay, so the last thing that we are going to see is always based on this first part. So I'm going to take it, copy paste it, and move it here at the bottom. Okay, So we will have this thing here. Now, in this moment, what I'm going to do, I'm going to decrease the resolution of this. Also, I'm going to hit F5 in order to have a different structure. So I will eventually reset, start recording, and create a new shape for this. Yeah, like this. Also, well, eventually let's do this. Let's try to have some kind of, yeah, like this. It's way more interesting to work with this kind of complex three-dimensional thing here, where the surface is basically generating branches and then blending together once again, so we can get, well, actually I think I have exaggerated a little. So what I'm going to do, I'm going to step back a little and reset, record, start. Yeah, I want this surface to separate into branches, but not as much as it was happening. So 0.15, we are back to the original. 0.22 was too much, so let's say that 0.18, 19 should work. So let's get rid of these, reset, record, and start. And I want this to split and generate branches at a certain moment. Let's see if this happens. Yeah, it happens towards the end, but it happens. Okay, let's see if we increase the amount of points eventually. This will give us more possibility of branching if we decrease these. Yeah, let's see what happens. This is the last try. Let's see if we succeed. Well, no, but it's okay. Let's work with this. Yeah, we have some branching here at the bottom, but it looks like a more interesting shape. Just remember that if you want some branching, in this case, you might want to work with any of the techniques that we already saw, or simply change the density of points of the populate 3D, and or change, for example, the threshold for the Metaball T. Okay, I'm not going to waste any more time in this, but you can easily achieve a whatever kind of result you might want to work with. Now, in this case, the problem is that if I start to work with an amount of 700 curves, the calculation that we are going to perform now, it's going to be very heavy. So I would recommend that you use a smaller amount of curves. So in this case, there is no problem if the set of curve come out very discrete, like in this case. So with huge separation, we are already getting 350. I would eventually decrease this a little more. So I'm going to do like, yeah, exactly. Looks sharp and more light, like 178. It's already a good set of curves in order to do what we are going to do right now. So what we are going to do now is eventually use exactly the same principle that we have been using so far. So we are going to give a charge to each of these curves here, and this charge is going to blend with the other charges, creating one single force field around this set of curves. And this force field will be used by Grasshopper to create one single mesh. Okay. In order to do this, what we are going to use is another plugin, which is called Cocoon, which is in the mesh toolbar. So we need to, first of all, we need to give charges to these curves, and we do it by using the curve group charge, not the curve charge, but the curve group charge. I'm not going into details in this case, but you can find out the difference by yourself or watching some tutorial on the web or whatever you want. Or you can just drop me a line and ask for a particular explanation, okay? But I won't waste time here during this tutorial. So curve group charge asks for a list of curves. Okay, now we are getting here a list of curves. Just double check this or simply flatten the input of the curve group charge. Okay, so you are sure that this is receiving one single set of curves. What happens with this curve group charge? It is asking for the radius and strength. What does it mean? It means that if we have a line like this, radius sets the radius of action of this charge. So we are giving a charge to each of these curves, and we want to define up to what radius, which is this one, this charge will have effect. So we are defining basically a volume, a pipe volume along each of these curves where these charges will affect the force field. Of course, once we have another line here and another line here, each of these lines will have a radius. So there will be this one which will have a radius, so they will overlap. Okay, this overlap area would result into double the effect of the charge. So in this area we will have 2 times the effect, in this area eventually 3 times the effect, and so on. Okay, but as we are using a curve group charge, this will not happen. Okay, so that's the explanation of why we are using the curve group charge. In the end, I ended up explaining it. But anyway, so in the end we will get a uniform force field all along this, let's say, virtual surface. Okay, so the radius in the end will define the thickness of the wall that we are going to create. Okay, so if we take a look from top view, you see that a thickness of 2, it's enough to have quite a consistent wall around these curves. Okay, so I would set this to 2.00, which is variable. We can also change it later on. And strength. Strength means inside this potential pipe of 2 millimeters radius, how strong do you want the charge to be? The stronger the charge, the more the mesh will fill the pipe volume. The smaller the charge, the less this pipe volume will be filled by the mesh. Okay. Of course, our interest is that the whole pipe is filled by this curve group charge. So I would set this to 5, for example. 5 is already quite a good value in order to create a continuous aspect for our mesh. Also consider that if we take a look at this from the front viewport, you see that if we are considering a radius of 2, so the action of this line will expand 1, 2 upward and 1, 2 downward. So we have enough overlapping for our curve charge in order to have one single mesh as a result. So here we have our curve group charge, which is just one charge, okay, because it acts on the whole group of curves. And then we take the cocoon component, which asks for 2 things basically, which is the ISO and cell size. And there is an execute component here, that input that simply fires the cocoon calculation. As this is very heavy, there is a dedicated Boolean value that you must turn on exactly by hand. Okay, so cell size is regards the size of the polygons of the mesh. Okay, so the smaller the value, the higher the resolution of the mesh. I always recommend to keep this value high in order to create a low resolution mesh, okay, at first, and then eventually start decreasing this value little by little in order to don't have your computer crashing. Okay, but the more interesting value is probably the ISO. Now, ISO here is exactly like the threshold of our metaball. So we are always dealing with the same behavior. Okay. So what I'm going to do now, I'm going to give this ISO a range between 0, 1, and 10. And as cell size, I'm going to use a slider set to, let's say, 0.50 up to 2. Okay, and initially I will give this value the highest value possible. Okay, so like 2 in this case. And I'm going to use a toggle. In this case, I'm going to use a false start toggle because this is another plugin. I will share the link in the description of this video, so you will be able to download it and install it in your Grasshopper. This is very interesting because this toggle returns to false each time you open your script, or you just, for example, if let's set this to true, and then I copy paste it and it pastes it as a false. You see it always returns to false whenever you don't need it, basically. So I will set this to false and plug it into the E. Okay, so now we are ready to fire the Cocoon calculation, and I'm going to hide the input curves, and I'm going to set this to true. You see that computer is hanging a little because Cocoon, as I told you, is requires quite a time-consuming calculation and process. But you see that we already have a result. We have very large polygons here because we have set the cell size to 2. Okay, so this is a bulky representation of our set of curves, which was very elegant, as you can see. So eventually what I will do, I would decrease the amount of the value of the radius in order to have a more thin walls. Remember that any change, any edit that you make while this toggle is set to true will make Cocoon calculate once again. So in order to have an idea, Cocoon took almost 10 seconds to calculate. So I would recommend to avoid having real-time calculation performed by Cocoon. So first of all, set this to false. Secondly, avoid having this part of the definition affecting Cocoon calculation by, for example, putting here a data dam in order to transfer data to Cocoon only if you want. Okay, so I will press play here, so the curves are transferred to curve group charge only when I want. Even if I change things here now, they won't affect Cocoon until I hit play once again. And yep, that's it, by the way. So in this moment I can change the radius to 1. This edit happens instantly because there is no calculation made by Cocoon. And then I fire Cocoon once again. Let's wait a little. Let's see if we start getting some thinner walls here. We should. And also, once we get this one recommendation, when you have Cocoon running, don't touch anything. Okay. Yeah, so yeah, we are starting to get thinner walls, but the thing that is affecting now our calculation is the ISO. Okay, so the lower the ISO, the thicker will be the mesh. Okay, so what I'm going to do now, I'm going to make this calculation lighter by increasing the cell size. Okay, so I'm going to decrease the resolution of the mesh in order to have faster calculation, and I will do this by turning Cocoon off, changing the range for our slider, setting this to the highest value possible, and then fire Cocoon once again. This will result in a lower resolution for our mesh, but it's more than enough for now, because I want to show you behavior of the ISO parameter. Let's wait for this to finish. Okay, you see that we have basically a nonsense, because having this cell size so big is actually not capable of giving us a continuous aspect for the mesh. But if I take, now you see that here we have this thick wall here. If I take this and increase it to 0.5, let's make this new simulation, new calculation. Unfortunately, there is no way of avoiding this calculation time by Cocoon. It's quite a time-consuming process, as I told you. You just have to be patient and wait. Sometimes Cocoon can hang for minutes until it gives you the final result. You see that the mesh already shrinked. Okay, so the higher the ISO value, the thinner will be the resulting mesh. Okay, so what I'm going to do right now is I'm going to create the final mesh. Eventually Cocoon will hang for a while, so eventually I will stop the recording and then get back to the video as soon as Cocoon gives us the final result. But anyway, I will turn Cocoon off, set the cell size to 1 millimeter. So you see that we have very small polygons in this case, and fire Cocoon once again. And you see that it is also taking time to react to the toggle switch, as you can see. But anyway, I will stop the recording and reactivate the recording as soon as Cocoon gives the desired result. So here we are. It took 42 seconds to create the final result, but you can see that we already have a nice result for our conversion into the final mesh. Of course, there are still gaps here, but you already know that you can simply increase the amount of curves. In this case, I wouldn't change the radius or the ISO, because I'm getting quite a nice result for the general walls of my mesh. But yeah, this is the primary elaboration from Cocoon. Now Cocoon outputs two things. Okay, first one is the mesh. So eventually I can bake this in order to maintain it visible here. So the first thing is the mesh, and the second thing is called refinement data. Okay, so this is used by another Cocoon component, which is called the refine. Okay, in order to create a let's say smoother version of this initial result. Okay, so how do we work with this refinement data? We simply plug them into the refinement data here in the refine component. Now this has 6 inputs that we must populate in order to have refine working. Okay, and also there is the enable execute input. So we just copy paste this false start toggle and plug it here. So it's already set to false, as you can see. And then we must populate these 6 values. Now, just in order to quickly populate these, I will set first 3 to 1 to 100. So like this. In this case, I won't go through the explanation of all these parameters here, while the last 3 will be between 0 and 3, like this. Okay, so when all the parameters are populated by inputs, you see that the refine starts to emit its output. Okay, and its output in this moment, when the execute is set to false, is exactly the same mesh as the Cocoon component. Okay, so once we have these things going, I would just take the sample tolerance and increase this value a little. And then I will fire the refine as with Cocoon. If things go wrong, I will just interrupt the recording and then switch it back on. Well, actually, it wasn't necessary. I was about to stop recording, but you see that we already have the result. So you see that this mesh looks way smoother than the original one. Well, actually, I can bake this result in order to have this comparison here easier. If you take a look at this with a rendered view or architect view, you see that this mesh on the left is way smoother than the original one. Okay, so in this case, for example, the hard work is being performed by Cocoon, while the refine is just smoothing or creating a higher resolution version of the original mesh. I can, for example, I will only give a quick explanation of these three components here, these three inputs here. Subdivision, of course, increases and somehow smoothens a little the mesh. So if I give one step of sub D, you will see that the resolution of the final mesh will increase. It will be evident because the wireframe representation of the mesh will be very dense. Yeah, you can see. I will also bake this in order to have it like visible here, like this, and I will switch back to our wireframe preview so you see how the wireframe is denser in this mesh than in the previous one. So in order to have an idea, I am getting now a mesh with almost 50,000 faces. And then there is the Laplacian smoothing. That is actually what it does. It tends to smoothen the mesh by, let's say, changing the position of the existing vertices of the mesh. Okay, so trying to smoothen the mesh by adapting the position of the vertices in order to avoid excessive inclination between two adjacent faces. Okay. And then there is balance passes. That is, in my opinion, is one of the most interesting thing that you can do in Cocoon. You see that we already have some kind of very interesting organic shape, like some alien thing. So balance, I normally, in order to explain it, I say that it tenses the mesh. Okay, it creates some tension in the mesh. So if I give one balance pass, you should eventually see how this mesh will start to get more like stretched. Okay, let's give it a little time to perform the calculation, and eventually we will see how this, yeah, you see how this is tensing the mesh a little. Okay, so we have let's bake this also, which in my opinion is the more interesting result that we can get right now. You see that this tension is actually giving us a smoother result in many aspects, not only in the position of the vertices, but also in the tension of the curves, the curvature of these holes, for example. Okay. And so you can see, for example, how we can, well, let's turn this toggle off and turn this off as well. So we don't have Cocoon calculating anything right now. So I will group this. This is Cocoon, Cocoon plugin. Add the group and move this, just the writing here. Cocoon plugin needed, and what I will do is eventually take a look at these results here with a shaded preview. You see this is the original Cocoon mesh. This is the first refinement, and then we have some subdivision going on, and some balance passes going on here as well. So it's quite interesting to see how we can convert metaballs into three-dimensional objects. And by the way, this object here, if we take a look in Rhino, is a closed mesh, so it is ready for production, even with 3D printing or whatever production or prototyping technique you might want to use. Okay, so this is a very nice way of converting metaballs, 3D metaball structures into three-dimensional meshes ready for production. Okay, so here you already have a quite a interesting and practical result for all this metaball theory. Okay, so that's it. That was the latest thing that I wanted to show you. Now you can of course play around with this definition that I will share with you. I will share the link in the description of this video. You can always drop me a line in case you have some particular problem, or you need some further explanation, or you have some questions and whatever. Just stay in touch with the website. Also, I would recommend that you follow my social network and professional network. You can simply find me online by using this nickname that I have on Facebook, Instagram, Twitter, and so on. You can find it. Oh, well, actually, yep, this is the way that it is made. Okay, so thank you very much for watching this video, and I hope you found it useful. Thank you. Bye.